Here we go. Okay. So uh, we're going to learn about how to graph sine, cosine. Um, almost tangent is here. Yeah, and also tangent. Okay, sweet. All right, so here are the key terms here: period, amplitude, midline, frequency, and phase shift. So let's define those terms first, and then we'll see how this works. So period. Period is the time, quote unquote, it takes to see one full curve. And we'll talk about what that means, the time part, and what does it mean to see a full curve. When I talk about curves, we're either talking about sine, cosine, or tangent. Now, what is the amplitude? The amplitude is the size of the wave. The midline is the horizontal line that divides that goes through the center of the curves. The frequency is the number of waves seen, I should say, number of full curves seen in the interval from 0 to 2 pi. And the phase shift is the horizontal shift of the curve. So these terms may have been may be familiar to some of you, or it might be the first time, and it may not seem so apparent as to what they really mean. So let's see how we can connect these terms to something visualized on a graph. And before I do that, I want to show you something. Hopefully it opens up. So I want to show you something on Maple on how the graphs of these functions that we're dealing with, right? How are they related to the unit circle? So we have to recall. So recall the unit circle. Like I've mentioned before, to understand to understand um, to understand trigonometry, you have to know the unit circle. So let me see if this is working. I think there's a mix-up. Okay, so if you recall, in the unit circle, the x values were given by what? Cosine theta. And the y values were given by what? Sine theta. And so let's just make this theta for now, so you won't get confused with x and y's. So y equals sine theta. So I'm going to call this theta for now, okay? Now, what do you guys remember about theta, about the angle, and the values of the angle when you plug in for sine? So you have to go back. So let's go back. And of course, we're going to use radians, okay? So these are things that we should know, sine theta, right? So at 0 degrees, or at 0 radians, I should say, what is sine? Does anybody remember? At 0 degrees, what is sine? Or in other words, go back to unit circle. Let's go back to unit circle. So I'm gonna draw a unit circle. A small unit circle. Remember when we start at 0? We start at 0, we're right here. And then what is that point associated with 0? Isn't it 1 comma 0? Remember what's 1 comma 0? Isn't this cosine of 0 degrees? Sine of 0 degrees? Which means that cosine of 0 is 1 and sine of 0 is 0. So we know from the curve, from the unit circle, when we start at 0, sine is 0. And then what other values do we know? Don't we know pi over 6, which is 30 degrees? Again, this is stuff that we should know already. We've created a chart about this already. Sine of pi over 6 is what, guys? Does anybody know? 1/2. Very good, Tiffany. And so on and so forth, right? Pi over 4. That's rad 2 over 2, right? Pi over 3, which is 60 degrees. That's rad 3 over 2. And then pi over 2, that's what? 1, right? And then what happens as you continue? So this segment here only talks about the first quadrant. What happens in the second quadrant? Like if we were to like write all of this stuff down, what would be the next corresponding angle that would be helpful here? So I'm gonna go every like 30 degrees, right? So then 30 degrees after 90 is 120, and that can be written as 2 pi over 3. And 2 pi over 3, because I'm in the second quadrant, guys, because I'm in the second quadrant, I'm still positive. And 2 pi over 3 has a what? The reference angle is pi over 3. And we already know what pi over 3 is. It's rad 3 over 2. So I'm going to have rad 3 over 2 again. And then the next angle would be 150, which is the same thing as saying 5 pi over 6. And what's 5 pi over 6? The reference angle is pi over 6, which is 1/2, and I'm in the second quadrant, so I'm still positive. You see that? And then what? And I continue on with this. I continue on. What is pi? What is sine at pi? At pi radians, or at 180 degrees, what is that going to mean? Isn't it going to be 2? Well, actually, sine can never be bigger than 1, because if you see the unit circle, right? The y values, the most that the y values could be is 1, and the most that, and the smallest it could be is -1. So always go back. Like I said, always go back to unit circle. Always go back to unit circle. So the values of sine are bounded between 1 and -1. So at pi, remember at pi, I'm right here. This is pi right here. So -1 comma 0, the y value is what I care about for now, because I care about sine. So the y value is just 0 again. So at pi, I get 0. And then I continue on. I'm going to try to complete the entire revolution around, okay? And then the next thing is what? After pi, I'm 30 degrees in front of pi, which is 7 pi over 6. And then I'm 7 pi over 6. Now what happens? I'm in the third quadrant. The y values are negative. My reference angle is pi over 6, which is 1/2, but it's negative. So it's -1/2. And another 30 degrees would be, so 180 to 210, and then it goes to 240 degrees, which is the same thing as saying 4 pi over 3 in radians. At 4 pi over 3, my reference angle is 60, which is pi over 3. I know what pi over 3 is. It's rad 3 over 2, but it's negative because I'm in the third quadrant, and so on and so forth. This becomes now 3 pi over 2, which is 270 degrees. 270 degrees, I am right here on this side here. And what's the y value here? The y value is a -1 for the point, right? So I'm going to have a -1 here. And I'm almost done with the whole revolution around. So 270 degrees, which is 3 pi over 2. If you add another 30 degrees, it would be what? 300. The reference angle is 60. And what is that in radians? 300 is 5 pi over 3. 5 pi over 3, the reference angle is pi over 3. And I know pi over 3 is rad 3 over 2, but I'm in the fourth quadrant. And if I'm in the fourth quadrant, sine is negative. And I'm almost there, guys. So then the last one is what? 330 degrees, which is the same thing as saying 11 pi over 6. And the reference angle is pi over 6, which is 1/2 for sine. But of course, I'm negative because I'm in the fourth quadrant. In the fourth quadrant, sine is negative. And then finally, when I get to 2 pi, I get back to 0. So that's what happens with my y values. Again, these are all the y values. These are the y values on unit circle. So what we're really doing, guys, is taking the unit circle and almost like separating the information into separate graphs. So we're looking at the relationship between the y coordinates on the point of unit circle and the corresponding angle that's made between the positive x-axis and the terminal side. That's what we're doing. We're comparing theta, which is the angle that's made between the terminal side and the positive x-axis, right? As you move around and theta gets bigger and bigger, what happens to my y values? It goes up, then it comes back down, becomes negative as much as possible, and then it comes right back to 0. So how do we show that? How do we show that on the graph? So watch this. So the graph is going to be what? I'm going to divide it into 4 equal parts. So that's normally what we're going to be doing. We're going to be dividing up our intervals into 4 parts, which relates to the 4 quadrants that we have. We have 4 quadrants, right? So what we'll see is that this is pi over 2, this is pi, right? This is 3 pi over 2, and this is going to be 2 pi. Okay. All right. And so at 0, what's sine? Sine is 0 here. So I'm going to plot a little point at the origin. At pi over 2, I know, so the ones that the smaller angles here are a little bit harder to figure out, but the point is that what are these x values? What are these values here becoming? They're becoming bigger and bigger until it reaches 1. At pi over 2, I got a maximum of 1. So I'm going to put 1 over here. I'm going to put -1 over here. So this is at the top here, at pi over 2. Then at pi, so I'm going to use this one here. Then at pi, my value of sine is at 0 again. Then at 3 pi over 2, I am all the way down to a negative here, -1. And then at 2 pi, again, I come right back to 0. And then you can fill in the dots in between. So for those of you who probably have seen this, right? If I connect the dots and I create a kind of a wave function, look what I get. I get something like this. Something that gets bigger, then gets smaller, and it becomes really negative. And this here, my friends, is a sine curve. It's one complete sine curve. So that's what I'm going to say here. This is one complete sine curve. And now, what happens if I continue going around the circle, around and around and around and around? I'm going to get the same curve again and again and again and again. So this is not just This is just one portion of the curve. But if I were to draw or I were to graph sine theta, right? This would just continue on. This would continue on forever and ever on both ends. Oops. I cannot draw, as you can tell. So I got something like this. This continues on forever and ever. It just keeps on going up and down, up and down, up and down. That's why it has a wave-like structure. Of course, it's very idealized, but this is the wave that we have. Now, what is my period? Now, in a sense, we can treat, right? We can treat the independent axis or the independent variable, which in this case is theta. We can treat it like time, right? So we can, I guess, we can make more of a connection with it. So the time here that goes by to see one full curve is 2 pi. That's how long, quote unquote, it takes to see one full curve. So the period for sine is 2 pi radians, or in other words, 360, is how long does it take to repeat a whole cycle, a full curve, a full cycle of a sine function. And again, a full cycle is just going around the unit circle once. That's all it is. It's going around the unit circle once. Okay. So any questions about the period? That's important. The period is going to come up again and again. So the amplitude is always going to be a positive number. So it's always positive. Even if so we'll see about how it could, like, we can have numbers in the front that are negative, but it's always positive. Because the amplitude is the height, quote unquote, of the wave. So what do I mean by that? I mean by, so first of all, before we talk about the amplitude, we have to really talk about the midline. So the midline is the horizontal line that divides or cuts through the center or divides the sine curve in half. So the midline is this x-axis. That's going to be my midline because it cuts through a half of the sine curve, right? It divides it in half, horizontally speaking. So the x-axis is, or the theta axis in this case, the horizontal axis is my midline. And then how do I write that as my midline? Well, it's a horizontal line, right? So to y equals 0. So y equals 0 is my midline. Now the amplitude is the distance between the midline and the highest point on the curve, or the distance between the midline and the lowest point on the curve. So what do I mean by that? If you draw this out here, right? This distance here, that's called the amplitude. This is my amp. That's how high or low my wave gets. So the amplitude is 1, and the same thing happens here, right? This is my amplitude as well. This distance here is also the amplitude, and my amplitude is 1. Okay, so that's all it is. Amplitude equals 1. Done. Now, what's the frequency? The frequency is how many full curves do I see in the interval 0 to 2 pi. So from 0 to 2 pi, how many intervals are there? I mean, how many curves are there? We only see one full curve. So we see that our frequency is 1. What is the domain of the sine function? Well, the domain here, right? This goes on forever and ever to the right and to the left. So the domain is all real numbers. So I can write it as an interval notation, negative infinity to infinity. And then what's the range of my function? Well, it's the y values, right? And the y values are bounded between the values 1 and -1. It can never be above 1. It can never be below 1, -1. So what do we say? We say that our range is enclosed in the interval -1 to 1. Okay. Any questions about the sine curve? Does this make sense? This whole so again, the sine curve represents the y values as you move along the unit circle in one revolution. My y curves are really, my y values are doing this. They're going up, becoming 1, then they're slowly coming down. They become 0, then -1, then finally 0 when I make a full revolution around. So that's how we get it. Okay. Okay. And so then because we can do that to the y values, we can also do that with the x values. So in this case, we're going to talk about cosine. So I'm just going to write cosine theta. And again, the y value here, I know it's could be a little misleading. So we're dealing with the x values of our unit circle, and we're transforming that into a graph. So let's do the same thing we just did for sine. I think in one of your homeworks, you're gonna have to do this anyways with the unit circle. So this is cosine of theta. So we're gonna go with from 0, pi over 6, pi over 4, pi over 3, and pi over 2. So cosine of 0, it's pretty much the same values, right? Remember we talked about this? It's the same values for sine, but then it's just that now we start with the 1 and we go in reverse order. So this becomes 1. This is rad 3 over 2, rad 2 over 2, 1/2, and 0. But now when we go on, so again, we can draw a little unit circle again, just to give us a reference point. So as I continue around, right, this is pi over 2, this is pi, this is 3 pi over 2, this is 0. So in the first quadrant, this is my first quadrant, right? These are the x coordinates on my first quadrant as I move around, right? It starts at 1 and then it becomes 0. But then what happens when I go to the next angle, which is 150 degrees, no, 120 degrees, pardon me. This becomes 2 pi over 3. And 2 pi over 3 is the reference angle pi over 6. And the x value, or I mean the x value, or the value for cosine would be -1/2 because I'm in the second quadrant and my x values are negative in the second quadrant. So everything will be negative now in the second quadrant. And then the next angle here would be 5 pi over 6, which is 150 degrees. And pi over 6 is rad 3 over 2, right? The reference angle, but I have a negative because I am in the second quadrant here. So that's negative rad 3 over 2. And then when I get to pi, what is the value of cosine at pi? -1. That is right. It's -1. That's -1 because the x values, right? We're looking at the x values as they move around the unit circle. The x value right here, because it's a unit circle, is -1, right? That's how the unit circle works. And then the next angle would be 7 pi over 6, right? 210 degrees. And then this becomes what? Negative. So pi over 6 is rad 3 over 2. So this would be also -3 rad, or negative rad 3 over 2. I'm in the third quadrant. The x value is still negative. And then I get the next one here would be 4 pi over 3. And pi over 3 is 1/2. So this will be -1/2. And then I get to the other angle here, which is 3 pi over 2. And what is 3 pi over 2? What is the angle at 3 pi over 2? What is cosine at 3 pi over 2? What's the x value of the point when you're exactly at this point here on the unit circle. It'll be back to 0. That's right. And then we work our way back, right? We're almost one full revolution. We're almost one full revolution. We're right here. And now we're going to go another 30 degrees or another pi over 6, which will give me what? 5 pi over 3. It's 300 degrees. Pi over 3 is 60 degrees, right? Which is 1/2. But I am in the, so okay, let me just write this down here. So from 0 to pi over 2, I am quadrant 1. Then from 2 pi over 3 to pi, I'm in quadrant 2. And then from 7 pi over 6 to 3 pi over 2 here, I'm in quadrant 3. Oops. And then 5 pi over 6, and then I get to 11 pi over 6. This becomes rad 3 over 2. And then finally, when I make one full revolution, so this is quadrant 4, when I make one full revolution, I start back at 1. So these are the values for cosine as I traverse the unit circle counterclockwise. So again, we're only looking at the x values. So now what do? We're going to plot the same thing again. We're going to do pi over 2, pi, 3 pi over 2, and 2 pi. This would be at 1, and this would be at -1. But this time at 0, when I start at 0, and I'm going to call this theta. When I start at 0, my value for cosine starts at 1. Unlike sine. It's unlike sine. So it starts at 1. At pi over 2, so I'm going to use this one here, 0.1. And then at pi over 2, what's my y value? What's my cosine value? It's 0. And then at pi, I'm at -1. And then at 3 pi over 2, I'm back at 0. And then at 2 pi, I'm back at 1. And then if I connect them in a wave-like fashion, I get cosine. So this is one full cosine curve. So in sine world, we see one little hill and one valley completely, right? In the cosine realm, we have half of the curve here of like the hill. We have a full valley in between, and then we got the other half of the hill on the right side. So that's what we have for a cosine curve. And again, this is only one revolution around the unit circle. That's all. This is only accounts for one revolution around. But I can continue moving around and around and around. So this thing here actually continues. It continues its course. The wave-like structure behind this, right? I think something like this goes down. Sorry, this should not be this. Do something like this. Goes down like this. Then goes up like this. And so on and so forth, right? So these curves, these are the cosine curves. This continues on and on and on. If you notice, the sine curve and the cosine curve are nearly identical in terms of the shape. It's just that one is shifted over, if you notice. If you were to shift sine and you're to shift it to the left by pi over 2 units. So if you shift it over pi over 2 units, you get exactly cosine. And the same thing, you take cosine and you shift it over to the right a bit by 90 degrees or by pi over 2 radians, and you get back sine. So sine and cosine are like almost the same thing. It's just that one is shifted over, and you can tell by that, by the you can tell by the values that they share the same values. It's just that they don't share the same at the same for the same angles. They don't, but they pretty much look the same. So now you tell me, guys, what would be the period, what would be the amplitude, and what would be the midline? It's pretty much what? So the period is how long it takes to see one full curve. Obviously, we only have to move around the unit circle, 2 pi radians. So the period is identical to the period of sine, which is 2 pi. What is my amplitude? Well, what is my midline first? Again, my midline is the center here. So this is my midline, and it's y equals 0. My amplitude is the distance between the midline and the highest point, or the midline and the lowest point. That's my amplitude. But my amplitude is just 1. What's my frequency? My frequency is the number of full waves made between 0 and 2 pi. And I just make one full wave, so my frequency is 1. My domain, right? This goes on forever to the right. This goes on forever to the left. So my domain accounts for all real numbers, negative infinity to infinity. And my range are all the y values. And the y values, again, are bounded between the same bounded interval as sine. It's bounded between 1 and -1 and everything in between. Okay. So those are so these are now going to be considered as our parent functions. So of course we're going to make this more in tune with what we usually do with functions in pre-calculus. We transform them, we vertically stretch or compress them, we horizontally shift, we vertically shift up and down. So this is when we're going to add up to the mix. But these are the parent functions that we start with. So we have to start and base our future endeavors with trigonometric functions based upon these two foundational graphs. So we have to know what cosine looks like as a parent function, just cosine of the angle, and sine. So any questions about this? No questions. Okay, let me see if this will work. Let me try to open up software package. It's just not working last time. Give me 1 second, okay. Now it's working. Okay. Here we go. Wait a minute. So a lot of these things are hard to bring out if I were just to draw them. So having some simulation actually works a lot in helping understand what's happening. So let me find out where it is. So let me show you what I'm looking at right now. I'm looking at Maple. And again, you guys can download this for free on CUNY, on the eMall. on the CUNY email that I don't know if you guys are aware of that, but I would recommend, and it's free. Where is it? Hold on, guys. I think I've seen. Yes, there we are. This is what I'm looking for. Okay, let me stop sharing and let me share the same. The other. Yes. So this is what I want to share with you guys. It's a little big. All right, so I want to show you this sine curve. I have to share with you another screen. Hold on 1 second. Yeah, there we go. Okay. So this is the sine curve. You see that? And like we've talked about, sine theta is opposite of hypotenuse, right? We have a right triangle, and we know the special values of sine when theta is 0, pi over 2, right? We just literally just wrote this out on the table. And I don't know what just happened, but the idea is that there should be a unit circle here. I don't know where it went. I think they changed it. But the idea is that when you rotate, this is rotate, right? Oh, there we go. There we go. You guys see it? So this is my unit circle. You see this right triangle? This is exactly what we wrote what we drew before. This angle here, this angle right here is the angle that's being presented on the horizontal axis. So let me slow this. I don't know if you can slow it down. I guess you can. But as I rotate around my unit circle, right? Let's reset. So you see at 0 degrees, I start at 0 because that's my y value. So again, these are the y values only for, for the unit circle. And as I traverse the unit circle, my y values get bigger and bigger until, boom, I hit pi over 2 where my y value is 1. Then I continue on. My angle, as you see, gets bigger and bigger. My angle is increasing. It's being bigger than pi over 2. And my y values are getting smaller and smaller until it reaches pi. When it reaches pi, when my angle, when my terminal side reaches pi radians, my y value becomes 0. And that's what I have as the graph. And my y values become more and more negative until it reaches -1 at pi over 3 pi over 2. And then finally, when it makes a full revolution around, I get right back to where I started at pi. And then this just continues again and again and again. Makes sense? I hope now this visualization gives you a better understanding of what I mean when I say when I go around the circle. These are the y values being traversed. That's all it is. These are the y values of my unit circle as I move around it. Okay, so that's that one. And then you also have cosine. And again, cosine is adjacent over hypotenuse. And again, we have the same values for the angles, right? From 0, pi over 6, pi over 4, pi over 3. And so in this case, I'm not looking at the y values anymore. I'm looking at the x values. So obviously the x value here is at 0 degrees, it's 1. And then when I rotate my x values, so this here, this little height here represents this red. I don't know if you noticed that. And the other one in the sign, right? You see this is green. So the green here is this side of the right triangle, which is the y values, right? But the red side of the right triangle represents the x values. So you see how the x values here are represented here? And the only thing that's changing along is the angle with the x values. So as the x values get bigger, as the angle gets bigger to pi over 2, my x value becomes 0. And then my x value gets bigger again but in this case, it becomes negative, right? My x values are negative. And then my x values get to become 0 again at 3 pi over 2. And then finally, it reaches back. My x values get positive again because I'm in the fourth quadrant. And my x values get a height of 1 again. So I hope you guys have this visualization now a little clearer in your minds and see the connection between sine and cosine. I always thought this was very helpful, and it's cool that there's a program like this that can help. All right. So what do you guys think? Does that make more sense as to what sine and cosine looks like? Yes. I'm glad. So yeah, it's hard to always to do that just by hand and for you guys to be like, oh yeah, I understand what you're talking about, unless you actually see it for yourselves. Okay, cool. So now let's talk about tangent. Let me just see what. Okay, let's talk about tangent. So what's up with tangent? Now, tangent is very different from sine and cosine because tangent represents what? So I'm gonna call this theta, right? Remember what tangent was also defined as? Isn't it defined as sine theta over cosine theta? So tangent is really sine theta over cosine theta. So it's like saying take the y and the x values for the unit circle and just divide them. And if you guys remember, let's go to theta. The special values for theta, right, are 0, pi over 6. These are like our reference angles. Pi over 4, pi over 3, and pi. And if you guys remember that table that we did with tangent, at 0, tangent is 0 because what is sine at 0? It's 0. Cosine of 0 is 1. So 0 over 1 is 0. So tangent is 0. What is pi over 3, pi over 6? Well, again, it's sine of 30 degrees or pi over 6 divided by cosine of pi over 6. Sine of pi over 6 is rad 3 over 2. And then you divide that by, pardon me, is a half. Sine of pi over 6 is a half divided by rad 3 over 2, and you get 1 over rad 3, or in other words, rad 3 over 3. Pi over 4 is 45 degrees. Sine and cosine are exactly the same, so when you divide them, you get 1. Then at pi over 3, you get rad 3 because it's rad 3 over 2 or for sine divided by cosine of pi over 3, which is 1/2. So you get rad 3 over just rad 3. And then at pi over 2, what happens at pi over 2? At pi over 2, sine is 1 at pi over 2, but cosine is 0. And when you get 1 over cosine, you get undefined. Remember, this is when undefined appeared. So actually, these are all the ones that we would need for now. So what makes tangent much different is that tangent has vertical asymptotes. So we're going to have something that looks like this. Yeah. And then the other asymptote will be here. So x, or I should say, yeah, theta equals negative pi over 2. So you're going to have something like this. Tangent is much different from sine and cosine. And the thing is, the period is also going to be truncated. It's not going to be 2 pi. it's actually going to repeat every pi units. So the period is pi. The amplitude, we can't really speak about amplitude because it's not really a wave. It does repeat, but it's not a wave, right? There is no maximum point because this is my asymptote. So we have vertical asymptotes. So note, tangent, the graph has vertical asymptotes. And the last time we talked about vertical asymptotes were when we were speaking about rational functions. And the period is pi, so that means if you notice, this is it. This is it. This is all, this is one full piece, I would say. One full slice. One full visualization of the tangent curve. So I'm going to see this again after 3 pi over 2, after pi units. So after pi over 2, you add pi, you get uh, you get 3 pi over 2 here. And then you do the same thing over here, right? This is going to be negative pi. This is going to be pi. And you get the same curve. Just repeat it again and again. That's tangent. The midline, you can say it's also y equals 0. The frequency, you can't really speak about the frequency because it's no longer from 0 to like this idea of the wave like is not the wave of the graph is not present in this scenario. So we're not really going to speak about frequency or amplitude for tangent, but the domain we are and the range we are. So the range is all the y values, right? And this assumes all the y values. So all real numbers, negative infinity to infinity. And the domain is a little weird to say, right? Because it's all the x values that are not, is not equal to an integer multiple of pi over 2 units. So n here is an integer. And so we're saying is that for every pi over 2 units, so pi over 2, this would be what? 3 pi over 2. This is negative pi over 2. And I would say n is an odd integer. It can't be an even integer. So n is an odd integer. So my domain cannot include the odd multiples of pi over 2. So 5 pi over 2, 7 pi over 2, negative 11 pi over 2. Those are the instances where we have vertical asymptotes. But everywhere else, we have my domain. So that's tangent. Let me see if I can show you tangent as well. So let me show you tangent, guys. So this is my unit circle again, right? As I move around. And then if I make this a little smaller, right? So I'm gonna rotate. And as you can see, as I move around, right? It just blows up because of the number getting really small. And then as you go around, again, it pops up again because my values get really tiny in the denominator. And so that's how tangent looks like when you do one full curve from 0 to 2 pi. You have an asymptote at pi over 2, and then you get these negative values here because x and y are negative, and then they become positive again in third quadrant because x and y are both negative, and then it becomes negative again because one of the x value is positive, but the y value is negative. So that's the the visualization of tangent from 0 to 2 pi as you make one full cycle around the unit circle. So again, the unit circle, and more about the unit circle. Okay. Hope that helped as well, visualizing it. All right, so now we have a good idea as to what our parent functions are in terms of sine, cosine, and um, tangent. So now let's look at what we can do in terms of transforming our sine functions. And so when we transform our parent functions, our sine, cosine, and tangent, particularly sine and cosine, they're known as sinusoidal functions. So this word sinusoidal is just a fancy way of saying transformations of sine or cosine. So for this one, this should not be sine theta. Let's do something different. Let's do something like this. So I'm gonna call this 3 sine plus 1. Actually, no, 2 sine plus 1. So make sure you make that little edit there. So I'm gonna write y equals 2 sine x plus 1. Okay. So what we're gonna have to start to do is find all these different pieces of information, right? All these characteristics of the function. We know what sine looks like, right? We know what it looks like exactly. We just drew it out. This is what sine looks like. But what happens when I do this kind of transformation? So first of all, what transformations have I applied? What are the transformations? So what's my parent function to begin with? Obviously, is y equals sine, right? Now, what's the transformations that I'm applying? There's only 2 of them that I'm applying. So what are they? So if I put a 2 in front of sine and I add a 1, what do these numbers here represent? What kind of transformations are we speaking about? So what does the 2 do here? What kind of transformation? Is it a vertical stretch? Is it a vertical shift? It's a vertical stretch, right? So I'm applying a vertical stretch by a factor of 2. So I'm stretching it by a factor of 2. Now, what is that 2 going to affect? Out of these different characteristics that we have, what is the vertical stretch going to affect or change? Which one of these characteristics of the wave is that 2 going to affect? Is it the period, the amplitude, the midline? Which one? Well, if you guys don't see it, it's going to be the amplitude. So the amplitude is affected by the vertical stretch factor. And then what is the 1 going to do? What is the 1? What kind of transformation is the 1, the plus 1? It's up by 1, right? So it's a vertical shift. It's a vertical shift up by 1. Now, what is that going to affect? The vertical shift up. Is that going to affect the period? Is that going to affect the midline? So I'm shifting sine and I'm moving everything up by 1. So the first thing that should change immediately is the midline. So the vertical shift up or down affects the midline. Originally, well, the amplitude is just the distance, so the amplitude is not going to be affected by the midline. What will affect, in addition, the vertical shift is the range. So again, guys, look what we're doing. What are we doing to sine? We're looking at sine and saying, hey, you know what? Let's double the amplitude. Instead of it being 1, I'm going to make it 2 now. So that's going to get bigger, right? It's going to get a bigger wave now. On top of that, I'm going to take that vertical stretched sine, right? On top of that, I want to shift all of it up by 1 unit. So that means that my midline now is no longer at 0. My midline is at 1. So let's establish that. So my midline here is y equals 1. That's my new, so I'm going to put 1 here, okay? So this is my new midline. And then my amplitude is 2. So I got 1, 2, that's 3. And then 1, 2, that's -1. Sorry, my amplitude is 2. What's my period? My period has been untouched, unfazed. It's still going to be 2 pi. My frequency, in addition, will also be unfazed. So my period and my frequency, right? They're tied together. They're in tandem. So if period changes, the frequency will change, vice versa. The domain is still going to be -infinity to infinity. Now let's see what happens with the range. So again, I'm going to split my period into 4 parts, as I've done before. I'm going to have at the midline, right? At 0, I'm going to start at the midline. So now we have to make that connection. At the midline, right, for sine, when I start at 0, I start at the midline. Sure, it's the origin, but I start at the midline. Same thing happens here. I start at my midline. Then at pi over 2, I get a maximum. I reach a maximum of 3 here. And then at pi, I get back to my midline. At 3 pi over 2, I'm at a minimum, right? My minimum here is the smallest y value that I can possibly be. And then finally, I get back to 2 pi. So this is my graph. This is my sine curve. Wonderful, complete sine curve. And of course, this continues on. Right? So I shifted up my sine curve. I also vertically stretched it. And even though it's not visually seen like a vertical stretch, because of the scaling, right? Because here I had every 3 boxes was 1 unit because I could do that here, but in this graph here, I couldn't necessarily make it every 3 boxes is 1. It would be I wouldn't have enough space. So that's why I kind of it looks a little smaller, but in reality, it's much bigger than the parent function. And then what would be the range now? The range is no longer -1 to 1. The range is from -1 to 3. So this range was also affected by 2 things. It was affected by the vertical stretch factor and the vertical shift, the vertical shift. So the range will be affected by the vertical stretch factor, which is the amplitude, right? And by the midline. So if the midline changes, the range is going to be changed. If the amplitude changes, the range will also be affected. Okay. So that's what we're going to be dealing with now. The inverse trig, we're not there yet. We're going to still continue with this stuff. So let me add an additional graph paper, square paper. Let's go graph paper here. Does everybody follow me with the transformations? Yes, so far so good. Okay. Now, so that's what happens when we change the vertical stretch. I mean, the vertical stretch and the vertical shift numbers, right? Now, what happens, for example, if I do this? Let's say I want to graph y equals cosine of 2x. So let me draw just an axis again here. Make this a little bit thicker. Okay. So I'm gonna make it every 4, right? I'm gonna make this pi over 2, every 4 here. Make this pi, 3 pi over 2, 2 pi. I'm gonna draw cosine for a moment, just for a moment. And then this is 4, 4, -1. Okay. And so what do we know about cosine? Cosine looks like this. It starts at a maximum and then it comes to 0. And then let me start using this. So this is max 0, minimum 0, maximum again. And then when you draw this, you get this curve, right? Again, this is cosine. So this here is the parent function, cosine. Just regular cosine of x. And these are my x values here. These are my y values. Okay. Now, what happens when I have cosine of twice the angle? In other words, what transformation am I applying here? There's only one transformation. But what is that transformation? What does that 2 represent? So remember, guys, what happens when you multiply the x value inside the function? What would that do? It's not a vertical stretch, because the vertical stretch occurs when the number is in front of the function, right? Like we saw in the previous example. You can't add numbers, because when you add numbers, that just shifts it up or down. So what happens when you multiply by 2 to the x of a function? What kind of transformation is produced? It's a horizontal effect, right? But it's not going to be a stretch, Daniel. Remember, this is when it's like the opposite of what you think. So you would think, oh, when you multiply by 2, it's a stretch. But when you do it horizontally, like such as this, it's actually a horizontal compression. It's a horizontal compression by a half, by 1/2. What does that mean? That means that instead of seeing a full curve in like this, I'm going to compress it by a half. So my new period is no longer going to be from 0 to 2 pi. It's going to be from 0 to pi. So the horizontal compression will affect what? The horizontal compression or stretch, but in this case it's compression, affects both the period and frequency. So that's what's going to be affected. So obviously the frequency here, remember we talked about the frequency? The frequency is exactly the number 2. So that's going to be easy. To find the frequency, it's easy. The frequency is the number in front of the x. So obviously when you talked about, for example, when we talked about cosine of x, right? The frequency is just 1. We talked about that here, right? The frequency is 1. Because I didn't have any horizontal compression or stretching. And we see one full cosine curve between 0 and 2 pi. That's what the frequency means. But now this 2 here, what is that 2 telling me? That tells me that from 0 to 2 pi, I'm going to see 2 cosine curves. So the frequency is just the number, is the factor, and or the coefficient is the coefficient of the independent variables. In this case, it's x, right? The independent variable is x. So my coefficient is 2, and that's the frequency. It's 2. Now, how do we find the period if we know the frequency? The period is always 2 pi divided by the frequency. So that's going to be the relationship between period and frequency. It's 2 pi over the frequency. So we get 2 pi divided by 2, which equals pi. So the frequency is pi. The frequency is 2. The period is pi. So how does that going to work? Now I'm going to divide this into fourths here. Remember, we're always going to divide our periods into fourths, into quarters. And so now I'm going to use a different color. I think purple will do. So I'm going to start at the maximum again, but I'm not going to wait until pi over 2 to get to 0. I'm going to get half of that, which is pi over 4, right? So I'm going to be here instead. And then a pi instead of being a -1 at pi, I'm going to be -1 half of that and half the time. And then instead of 3 pi over 2, I'm going to be where? 3 pi over 4. I'm going to come back to 0. And then instead of 2 pi being where I get 1 at, I'm going to get 1 again at pi. So look at this curve. You see that? And I'm going to do the same exact thing for the next interval here. So guys, this is y equals cosine of twice x. I hope you guys start to see this. This does get very complicated, especially when we talk about horizontal shifts. That's when we get crazy. But I want you to notice that this 2 here says what? Horizontal compress. So now instead of having this, think of this like a little spring, right? I just compressed it. And now I see 2 of them within that same interval from 0 to 2 pi. That affects my frequency, that affects my period, but as you can tell, my amplitude is still the same. My amplitude is still 1. I'm still only going, and my midline is still going to be what? My midline is still y equals 0. my domain is still negative infinity to infinity. My range is still negative 1 to 1. And again, and we can change this number, right, from 2 to 3. And so for 3, you'd have 3 of these cosine curves. And if you have 100x, cosine of 100x, you would have 100 of these curves between 0 and 2 pi. So that's how we do compression. For cosine. So does everybody follow this? Is it understood? So that's what makes trig a bit difficult, right? Because there's so much behind it. There's so much associated with it. There's the aspect of right triangles. And so you're dealing with the right triangles, sine, cosine, SOHCAHTOA, right? And then all of a sudden you have unit circles connected to those right triangles. And then we were able to get more values for sine, cosine. And then once we unravel the unit circle, we have the curves for each of those functions: cosine curve, sine curve, tangent curve. So then there's a lot of connections that are being made or should be being made as you're learning this. So that's what makes trig difficult, because there's the algebra aspect of it, right? We have Pythagorean identities, Pythagorean theorem, Pythagorean triples, um, radicals, rad 3 over 2, rad 2 over 2. You have to deal with that algebraically speaking. And at the same time, there's this geometric aspect of it with the unit circle and these curves and transformation. So really, trig brings everything that you've been learning so far all together. So I understand it could be sometimes a bit difficult in the beginning to get everything at once. So let's do the same thing now, but let's do the following. I'm gonna do sine of 1/2 x instead. So in the previous example, we did cosine of twice the independent variable, which is x, 2x, and it was a horizontal compression by 1/2. So what is sine of 1/2 x? What kind of transformation am I applying here? It's a stretch. And what kind of stretch? It's a horizontal stretch by what? By a factor of 2. So let's look at that. So I'm gonna make every 4, right? So this is gonna be pi over 4. No, pardon. This will be pi over 2, pi, 3 pi over 2, 2 pi, right? So I should be able to see, and I'm gonna call this this is 1, and this will be -1. So if I draw a sine, what is sine? Sine is something like this, right? So I move up, then I go down, go up, down, and then let me extend this a bit further. And then if I continue on, what's going to happen? I got 4, 4, 4, and I got another 4 here. I'm stretching it by a factor of 2. So what does that mean? What is my frequency? And consequently, what is my period? My period is 2 pi divided by the frequency. So what is my frequency, guys? What does that number here represent? 1/2. It's exactly the frequency. So what does that mean? The frequency is 1/2. What does that mean? The frequency being 1/2 means that I see half the sine curve from 0 to 2 pi. Normally, I would see 1 full curve from 0 to 2 pi, right? But in this case, now I'm going to see half of it in 0 to 2 pi. So what is that going to look like? So I'm going to see, instead of pi over 2, right, being at 1, I'm going to see it at pi. Instead of at pi having 0, I'm going to see it in twice as much, at 0, at 2 pi. So this is going to be the first half of it. And then I'm going to have the next thing is going to be what? So this will be double. So this will be 4 pi. This will be 3 pi. This would be 5 pi over 2. And this would be 7 pi over 2. So I'm going to have this here. So I'm going to double it, right? And this becomes at -1. And this comes back at 4 pi. So this is what I have instead. You see that? And then we can make this somewhere. So this is normal. This is the normal parent function, y equals sine of x. And this is y equals sine of half x. And so the period here is, so the frequency is 1/2. The period is 2 pi over 1/2. But when you divide by a fraction, you multiply by the reciprocal. And so that's why you get 4 pi instead. So my period is 4 pi. Every 4 pi units, I see only one sine curve. And everything else is intact. The amplitude is still going to be 1. The midline is still going to be y equals 0. The domain is still going to be -infinity to infinity, and the range will still be -1 to 1. All right. Any questions about horizontal transformation, stretching, and compressing? So again, this number here, right? This number is giving you the frequency, and it tells you whether you're stretching it or compressing it, horizontally speaking. And if you have a fraction less than 1, you're stretching. If you have a number bigger than 1, you're compressing, which goes against our intuition that would say that, for example, when you multiply by 2 instead in front of the function, you have a vertical stretch, obviously. But in this case, it's not a stretch, it's a compression. And in this case, it's not a compression, it's a horizontal stretch. Okay, now what happens if I start putting things such as this all together? So what happens if I get something like this? -2 sine of 2x plus 1. So what happens here? Can you give me transformations? And there's several here. There's several. So what are the transformations that are given by this function? What's the first thing that pops out? Right. So that negative is important. That negative is a reflection. Right. So we have reflections. So now instead of having a sine curve that goes up, down, up, we're going to have that flipped. It's going to go down, up, and then down. So it's an inversion. So it's a reflection across the x-axis. So that represents that negative sign here, that negative. That's the first thing. What's the second thing? Horizontal compression by 2 and a vertical shift by up by 1. Okay. So there's a horizontal compression. So the horizontal compression is not by 2, it's by a half. That's another weird thing about factors. The factors of horizontal compressions is by a half. You're cutting it in half. But I know it says 2, but it's 1 over that number. And then there's a vertical shift by 1, and there's something else we're missing. Vertical shift up by 1. There's another thing. What is that other thing that you're missing? There's another 2 that's there, right? In front of that negative. So what does that 2 tell us? So this would be the third transformation. This would be the fourth transformation. So we're missing the second transformation. It's a vertical stretch. That's right. That 2 here represents that vertical stretch. So this is a vertical stretch by 2 units, by a factor of 2. So let me add one more. So we're going to take all of this. Let me just cut this over here. And let's just put it on the new page. Okay. So this will be the last thing we do today, and then you'll have the quiz. So again, I'm just going to briefly draw this is 4 pi root 2 pi 3 pi over 2 2 pi. And then this will be 1 -1. I might have to make a few more, something like this. Okay. So sine, what does sine look like? Sine looks like something like this. This is a regular sine, right? This is our regular sine curve. But now what are we doing? We're going to be stretching it by 2, flipping it. So flipping it first, stretching it by 2, compressing it by 2, and then shifting it up by 1. So then we can do all those things individually, but let's just try to see if we can do that quickly. So that vertical shift up immediately changes the midline, right? Y equals 1. And then I'm going to flip it. So I'm not going to go up and down and up. I'm going to go the opposite. I'm going to go down, up, and down, right? And on top of that, I'm stretching it as well. So this would be a stretch, but then I'm flipping it. So it's going to look something like this. And then I'm going to be shifting it up by 1. So, and I'm compressing it by 2. So that means that I'm going to see one full curve from 0 to pi. So I'm going to have to divide this up a little bit further. So this is going to be my full curve. It's going to go from here to here, right? I'm not going to go. So my new amplitude is 2, right? So my amplitude here, this would be my first piece here. My first half would be something like this. Then I'm going to have 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. This would have to be the other point here. Whoops. So the graphing part of this is not that straightforward all the time. This would be what? This would be 3, because this is 1, this is -1. So now my amplitude is 2, right? So then this is my midline. I still have to go up. My maximum here will be at 3. And this will be my new curve. And then I'll just have this repeated again, right? This will be repeated again. So this is going to be my new curve. Y equals -2 sine of 2x plus 1. What's my frequency? My frequency is 2. What's my period? My period is pi. What's my amplitude? My amplitude is 2. What's my midline? My midline is y equals 0. What's my domain? My domain doesn't really change much. It's always going to be -infinity to infinity. But what's my range? My range will change a lot. My range, because of my amplitude and because of the midline, it's -1 to 3. And so that's going to be the transformation of my sine function when I apply all these transformations. I have a reflection across the x-axis. I vertically stretch it by a factor of 2. I compress it by a half, and I shift it up by 1. And this is the result. Alrighty. Okay. All right, so I'll stop here.